charges and magnetism. Let me recall some standard formulae of the concept. The formulae, these are the formulae. This is the formula on the force exerted due to the action of magnetic field on the moving charge. That is the magnitude of force exerted by the action of a magnetic field on the moving charge, where Q stands for magnitude of the charge and V stands for velocity with which it is moving, and B, it is a magnetic field applied on this charge. Theta is the angle between the two vectors, the velocity vector and the field vector. B is a magnetic field vector. If the charge is positive, is moving in this direction, if you apply magnetic field on this charge in the direction perpendicular to the plane like this, magnetic field in the inward direction. If you apply magnetic field like this on this charge, it is moving in this direction, the force arises on the charge, it is in this direction. It is in accordance with Fleming's right hand rule. The force exerted in this direction. This is velocity vector, this is a force vector. When you apply magnetic force or magnetic field on this moving charge, if it is positive charge. If the charge is negative, it is moving in the same direction. If you apply the magnetic field in the same direction like this, the force operates in the opposite direction. The force in the opposite direction. We have two vectors, F and V, velocity vector and force vector. The resultant of these two vectors will keep the moving charges in circular motion. The positive charge, it will circulate in this anti-clockwise direction, circular motion. If the charge is negative, it will circulate in the clockwise direction like this. That is the difference between the charges if they possess. Magnetic force, because that is always perpendicular to the velocity vector and magnetic field vector. The magnitude of force which arises, it is given by this equation. And the next equation, it gives the magnitude of force due to the application of magnetic field on the current carrying conductor. The current carrying conductor like this. When you apply magnetic field, on this current carrying conductor, it produces force. Of course, it is also called a magnetic force. The magnitude of force is given by this equation. It depends on what magnitude of field is applied and what current is flowing in the conductor and length of the conductor, where theta stands for the angle between B and L. That is, L is always a straight line like this angle. That is, a diagram shows that if the current, a straight conductor in which the current is in this direction, that is positive charges are flowing in the conductor in this direction. If you apply magnetic field perpendicular to this plane, like this, in this direction, perpendicular to this direction, inward direction. The magnetic force arises on the conductor is in this direction. That is the force acting on the conductor will be directed in this direction. This again the same Fleming left hand rule can be applied to find the direction of a magnetic field, magnetic force. If you apply field in the same perpendicular direction but in the outward like this, that is the direction, field direction is like this. On this conductor, the force will operate in the opposite direction. This symbol indicates magnetic field is perpendicular to the plane outward. It is perpendicular to the plane inward. Difference. The force which pull the conductor, it is directions are like this, magnitude. And the next equation is B stands for magnitude of the magnetic field or intensity of the magnetic field which is produced at a point. There is a point at the center of a coil. The coil is a circular wire of radius r. If a current is flowing through the coil, I is the amount of current. At the center of the coil, B stands for what amount of magnetic field arises due to flow of current in this circular motion of radius r. Mu naught I divided by 2r. R stands for radius of the circle, radius of the coil. If the coil has only one wire, that is single turn, this equation holds good. If the coil contains multiple wires or multiple turns, for n number of turns, we need to multiply this by n. So equation for the intensity of magnetic field at the center of the coil is, this is 1 mu naught n I divided by 2r. N stands for number of turns. Magnetic field at this is also a function of number of turns and number of wires in the coil. And the next equation is the equation B. It stands for magnitude of magnetic field at any point along this line. This line is the axis of the solenoid. At any point along this line, solenoid, as you know, it is the winded wire. What is that? Winding of wire around the cylindrical shape. Wire is wounded around the cylindrical shape. It is called as solenoid. When the current is flowing through it, we always see that magnetic field is produced along the axis of the solenoid. The intensity of the magnetic field at any point on the line is given by this equation, mu naught, constant of the magnetic field. N is the number of turns per unit of the solenoid, per unit length of the solenoid, number of turns per unit length of the solenoid. I is the current strength flowing through the solenoid. So these are the equations we have set. Let us see what types of problems we can expect on these equations. First equation, the first problem, proton is moving with velocity, V stands for velocity, this velocity meter per second. It is moving in perpendicular direction to the magnetic field. Magnetic field applied is 0.1 Tesla, 0.1 Tesla. If that is the case, find the force exerted on the proton. If the proton charge, that is the proton charge is known to us 1.6 in 10 to the power of minus 19 coulomb. What is the amount of force? What force arises on the moving charge? The charge is positive charge. This is positive charge with this velocity. It is moving in this field and the angle between these two vectors is 90 degree perpendicular distance. What force we need to calculate? That is, we have to use this equation. The force exerted on the moving particle due to action of magnetic field. F is equal to equation. All these data are given. Q equals the charge on the particle. Proton is the particle. And velocity of the particle is this in SI unit. Straight away you can substitute this value. This is the velocity of the charge. And the field applied in Tesla in SI unit is 0.1. And sin theta means theta is 90 degree. Here said perpendicular 90 degree between the two vectors. Velocity vector and field vector. Sin 90 equals 1. Upon this is a substitution. Upon simplifying this, we get this value. That is 8 into 10 to the power of minus 14 Newton force. This amount of force arises or will be exerted by the application of the magnetic field. What is the magnetic field? It is the amount of magnetic field on this moving proton particle. And the next problem is, it is a metal wire of length 7 meter carrying a current of 6 ampere is placed in the magnetic field Tesla. Calculate the magnetic force arises on the conductor, and the conductor is placed at an angle of 30 degree with the field. The equation for this is F equals, this equation for the force on the conductor, BIL sin theta. B value is mentioned 0.1 Tesla and I value is given 6 amperes. L value, length of the conductor, because force also a function of the length of the conductor. 7 meter in SI, write in 7 meters. 0.66. L is 6. It is not 6, it is 7. 6. L equals 7. And the theta is the angle between the field vector and the wire. It is in straight line, that is 30 degree. Sin 30, it is 1 by 2. So this, upon simplification, we get this value. 2.1 is the value. It is in Newton. This amount of force, magnetic force, will be exerted on the conductor carrying that amount of current. In that field, it is aligned with an angle of 30 degree. Yep. And the next problem is, here this amount of current 5 milliamperes is passing through a coil of 10 turns. This coil produces the magnetic field of this strength at the center of the coil. If that is so, what would be the radius of the coil? That is problem is. The equation for this concept is this. B is the intensity of the magnetic field at the center of the coil is given by this equation for n number of turns. But this value is given, this value is asked. Rewrite the equation as R equals, we get this formula. Given all these values, B value, substitute for these. R equals 2 into B value given, and mu naught value in SI, which is known to us, to 4 pi into 10 to the power of minus 7. N stands for 10 number of turns and value of 5 in milliamperes. You have to write it in SI. It is milli means 10 to the power of minus 3, 5 meter difference. Simplify this, we get this value in SI, 0.5 meter. What would be the radius of the coil? If for this data, radius of the coil is 0.5 meter. So this is what the problem and the solution of this is. And the next problem is the last one here. Listen. Here the problem is, we have a two conducting wires which are in parallel and straight. Two straight conductors which are in parallel. The wires that is named as A and D. One wire is A, another wire is D. A long wire, infinite length. They are always aligned in parallel and straight. Carrying a current of, one is carrying a current of 8 amperes. That is 8 amp for this and 5 amp for this. And both the currents are flowing in the same direction, arrow direction like this. And these two conductors are separated by a distance of 4 centimeter. That is, distance of separation between these two parallel lines is R equals 4 centimeter. And asked us to calculate what force will be exerted. There are two conductors. They asked only what is the force exerted on this conductor. And this conductor is not asked. What is the force exerted on this conductor and what length? Here 10 centimeter section of the wire, because force also depends on the length. On 10 centimeter of this conductor, what amount of magnetic force exerted? That is calculated. So concentrate on this conductor. That is, force exerted on this conductor is equal to equation, standard equation IBL sin theta. Let us assume theta equals 90 degree. What I mean is understand later. If theta equals 90 degree, sin that is becomes 1 IBL. About this conductor, that is current in that conductor, let us say IA. And the length of the conductor, that is 10 centimeter, we are taking a section of the wire 10 centimeter. L is LA and B. What is the B? Here magnetic field is not applied, but magnetic field there. What magnetic field is there? B is a magnetic field is there around this. What magnetic field? It is an induced magnetic field by this conductor. As you know, any conductor induces magnetic field. Let us say B is the magnetic field that is on this conductor applied. It is by the induction by this conductor at this point. What is the magnetic field at this point? It is induced by this conductor. That is magnetic field by this conductor BD. B equals BD. It is given by this equation mu naught ID divided by 2 pi r. It is in accordance with Biot-Savart's law or the Ampere circuit law. You can see that at this point, what would be the amount of magnetic field induced by this conductor? Distance of r. Or is the distance? It depends on the current in the conductor and r distance of separation between point and the conductor. This is a point. And the B at this point and any point on the line will remain same because the current in the conductor is uniform 5 ohm all over. So any point on the conductor B value remains same. That is a BD at this point, let us say distance is R. It is perpendicular distance between this point and this point R. This is the amount of magnetic field at this point. It is of course direction, that is the magnetic field magnitude. The direction is in accordance by Savart's law. It is perpendicular to the point like this to the plane as well as line in the outward direction. That is in accordance with Savart's law. That is the direction. Amount is magnitude is this equation. You have to put this equation into this. B equals this. It is induced magnetic field on the conductor. Magnetic field. The overall equation is this. What is the amount of force exerted on the conductor of 10 centimeter? It is requires substitution for these. Here what is IA? Current in the conductor A. Length of the conductor 10 centimeter, 10 into 10 to the power of minus 2 in meter in SI unit. Mu naught value is 4 pi into 10 to the power of minus 7. ID value current in the conductor D 5 amperes, 2 pi R, and R value is 4 centimeter, 4 into 10 to the power of minus 2 in SI unit meter. Here pi cancel and 4 2 has cancelled. What is that? And find what is that? Final value upon simplification we get 2 into 10 to the power of minus 5 Newton force. What is this force? This is 2 into 10 to the power of minus 5 Newton. It arises or exerted on this conductor of 10 centimeter. Of course, it will in this direction towards right direction because right hand, Fleming's right hand rule says that the force exerted on this conductor is always towards this conductor. Like this, it moves. The force will pull this conductor in this direction like this. What is the amount of force? This is the amount of force by 10 centimeter of the conductor. This is how we can solve the problem. Most important is we need to put this data into the graphical representation and recall the standard formula of that concept. Substitution and solution will be easier if you do it so. So with this we have completed this set of problems. Thank you.